Okay, I'm going to give a quick sketch of the divergence theorem proof. And I just want to note that it's actually quite similar to the 2D Green's theorem proof, which I'll link to in the description in case you wanted to look at a simpler version of what's going on with here. So here's how I will do this, and you will probably not see a proof like this, but I think it's the simplest way to do this. So let me just recall what the divergence theorem is again. It says that del dot f, the volume integral, is actually equal to an integral over the boundary. It's a surface integral. And you take the flux. Remember, the ds is shorthand notation for n times the surface area element. So here's what you do to do proofs like this is you simplify. So you take general f's that look like PQR, and you simplify to P0, 0. You set everything to 0 except for one component. And that's the first simplification. The second simplification that you used is you look at the domains. So you look at, if you have a general domain that looks nasty and kind of difficult to integrate, what you do is you should reduce it to a box. And I'm going to do the simplest box where this is the origin and all the sides have length 1, so it's just a cube. And so it turns out that these once you can do these simple cases, the general cases will follow just by symmetry, and by symmetry in this case, and in the second case it's by approximation, right? Because you can do the usual procedure of defining a grid of cubes. So you do approximation by cubes, and because it holds on each cube, I'll explain a little bit why this network of cubes, it also works. What happens effectively is there's cancellation on the edges, and so that links these cubes together in a nice way. So let's just do this in the simplified situation to see what's actually going on here. So we want to show the following equation. So the divergence is actually just px. And our flux integral remember it's f dot n ds, and we're on this box. So the normal vector is point out. That's our convention. And remember f, I'm going to draw f in the x direction. Notice that f is perpendicular to everything except for these two. On these two faces, the x equals 1 face and the x equals 0 face, that's it. So it's the x equals 1, or I'll just do x equals 0 plus the x equals 1. So let's just actually write out what these integrals are. These integrals are, it's the integral over x equals 0, and we have our y and z integration. And it's, of course, f dot n. And why is this our ds? Well, this is our ds because the area element, well, remember you use like RU cross RV, right? Well, this is actually the simplest scenario, and this turns out to just be 1. Because we just choose R to be the usual coordinates. So it's just, in the x equals 0 case, it's just 0, y, z. And we'll just choose u equals y, v equals z. These are the best possible coordinates to use for that surface, x equals 0. So, of course, RU, that's just j. This will just be k. J cross k equals I. The length of I is 1. And so you just get dy dz. So this is exactly what you would hope for. In other words, that's all I'm saying. So don't get worried about the ds calculation here. But now f dot n, let's just do that really quickly. This is going to be p00 dot n. So in other words, it's going to be the x component of n times p. So what's n? So so n in the x equals 0 case, let's just look. It's that vector, right? So it's just negative 1, 0, 0. Let me just label x, y, z here to clarify what these variables are. So it points in the negative direction, right? Whereas if we look at the x equals 1 case, it should point in the positive 1 direction. So therefore, for this x equals 0 term, this should just be negative p. And for the x equals 1 term, it should be a positive p. So in other words, the flux integral is equal to your x equals 0 part, your x equals 1 part, and you will have negative p. Remember, the x equals 0 has a negative pointing normal vector. And then it'll be a positive p for x equals 1 because the normal vector is positive pointing. And everything is just over your... I won't write the y and z limits. They should be obvious because it's a cube, right? So, and it's important to note that p is evaluated at x equals 0. P is evaluated here at x equals 1. All right? So note I'm going to group this together suggestively. So this will be the y, z ranges. It's a cube, right? So they just go from 0 to 1. So this will be p at x equals 1 minus p at x equals 0 dy dz. And whenever you see something like this, which is really just the same thing as p evaluated from x equals 1 minus x equals 0, you should immediately think fundamental theorem of calculus. Well, that's exactly where the left-hand side is coming in. So now we're going to link this to that left-hand side, px dv. So I'm actually just going to do that integral. So px dx dy dz. Remember, everything is now from 0 to 1, 0 to 1, 0 to 1. I'll just include those ranges. So let's just do that iterated integral, at least that first one. By the fundamental theorem of calculus in 1D, remember, you should always think of divergence as a 3D fundamental theorem. It turns out it's linked to the 1D in this way. It's just the integral over the y and z ranges of p evaluated from x equals 0 to x equals 1 dy dz. That is exactly what we have here. And so you see that we see where this is coming from. It comes from the integral over derivative, but it also comes from two surface integrals with different normal directions. So these two different normal directions, they actually correspond, they actually lead to the derivative because they have an inherent subtraction going on. So that's the essence of the divergence theorem. It's like the fundamental theorem of calculus on one side of a cube. I think that's worth writing down, just to emphasize. So it's like the fundamental theorem of calculus in 1D applied to one side of a cube in 3D. That is the divergence theorem. The essence, at least. So now that we have the divergence theorem in the special case P00 and cubes, let's briefly describe how we now generalize. So if we're going to generalize from P00 to PQR, let's just note that 0Q0 and 0R, they should behave similarly, right? By symmetry. All sides are equal. There's no difference between the x side, the y side, and the z side, right? So by the exact same logic that we used here, we should get the exact same result there. So in other words, we'll have an integral with qy, we'll have an integral with rz. It'll be the exact same idea, right? So therefore, just add everything. Just add them. So you'll have a qy, you'll have a px, you'll have an rz. You add all these integrals, and you still get f dot n. You still get f dot ds in all the cases. And so that gives you the divergence theorem on a cube. So now let's go from a cube to a general region. And so as I mentioned, the idea is you just make a grid of cubes and you approximate that general region by cubes and you take a limit. I won't go into that. I don't think it's important for practical purposes, but I will describe why you can patchwork, why the patchwork works. Why patchworking, why it gives the correct integral. So here's the idea. It's because of cancellation. On adjacent sides. So what do I mean? So I'm going to draw a case of two cubes. So if we want a rectangular prism, we split it into two cubes. So let me try to draw a rectangular prism. So what I'll do is I'll split this into two cubes. Let's pretend, for the sake of our argument, that this is a cube. And we have another cube. Supposedly. And we're doing two surface integrals now. So we have normal vectors pointing out in all directions. So how are we going from here to here? Let me just illustrate that really quickly. So I'll do it like this. I'll suppress the integrand, and we have our integral over our rectangular box. What I'm doing it now is I'm splitting our triple integral into a cube plus another cube. Right, that's legal. There's no calculus here. This is just splitting the integration domain. So now I'm going to apply divergence theorem to the cubes. Because we just did that, right? This is legal to do. So this is going to be a surface integral over a cube. And you'll have another surface integral over a cube. Okay, so now now what we're going to do now is we're going to combine into one surface integral. And here's the idea. The key edge is this edge right here. The one where the splitting happens. Okay, so the integral over this edge, it turns out it'll be exactly opposite to the integral over that edge. So if I call this edge, let's say like S0, and I call this one S1, I claim that the integral over S0 plus the integral over S1 is actually 0. And the reason is because N0 has a positive direction, whereas N1 has a negative pointing direction. So these integrals are exactly the same, but they have the opposite orientation. So therefore they cancel. And so because of this cancellation, you add the remaining sides. So if we remove that side, we now have surface integrals. Oh, I'm sorry, it's not a closed integral anymore because we just deleted a side. So now we have surface integrals over these boxes with empty sides. So now we just combine it. Into one integral. And notice it's actually closed now. If we add these two boxes together, it's actually just a closed surface, right? That's exactly what we want. So again, I'll link to the 2D video because this might be kind of hard to visualize. I think it's a little easier to visualize in the 2D case. So if this is a little confusing, I would check that out. But this is the heuristic idea of how you prove the divergence theorem. Hope this was helpful. Thanks for watching.